Today we're looking at notes DD-4 geometric series. So you should be familiar with this formula for an infinite geometric series. We've looked at it in a previous lesson. So S equals A sub 1 over 1 minus R. Okay, and so what we're going to talk about today is the different possibilities and why. So we say that a series, a geometric series, converges if the series approaches a unique number. So graphically, remember when we're talking about geometric sequences, we're talking about exponential graphs. So graphically, if a series converges, it would look like one of these two possibilities, to where as x is going to infinity, all right, our y values are approaching this value here, okay, or here. Okay, they're getting closer and closer and closer to 0 in this case, without ever touching 0, but it's going to approach 0. Okay, this happens when the absolute value of r is less than 1. Then the series is said to have a sum. Okay, the series has a sum. We also have the case where the geometric series diverges. So it doesn't approach a unique number. Look at what's happening in both of these graphs as x goes to infinity. As x goes to infinity, this number is going to keep getting larger and larger and larger and larger and larger exponentially. And this value for this specific graph is going to keep getting smaller and smaller and smaller and smaller. It's not approaching a number, it's just going to keep getting smaller. And this occurs when that common ratio, the absolute value of r, is greater than 1. We say that the geometric series has no sum in this case. It's a divergent geometric series. And this makes perfect sense because if you're going to keep on multiplying by a value greater than 1 to get to the next number, of course that's going to keep increasing and increasing and increasing, and there's no way to sum that value up. Okay? And this also makes sense because if you're multiplying by something like a half or a third or 2/3 or something like that, something less than 1, then the number is going to keep getting smaller and smaller and smaller and smaller and smaller until, it can't get much smaller anymore, okay, and it's going to approach some value. Okay, so what we're working on are 3 examples today from the book, page 596. And the directions are to find the sum if possible. If not possible, explain why. So look at number 71. So we have here our sigma notation. Our lower limit is n equals 0. Our upper limit is infinity. Okay, with our explicit formula here. Okay, so using our S equals formula, our geometric series formula for the sum, okay, we need to find out what r equals. We need to find out what a sub 0 equals in this case. And then from there we can plug in and find out the sum. So this value here obviously is our r value. Okay, so r equals -1/2. We want a sub 0 in this case. Okay, so plug in 0 here, so it would be 5 times -1/2 to the 0 power, and anything to the 0 power is 1. 5 times 1 is 5. Okay, and then we can go ahead and plug in to our S, our sum formula. So S equals 5 over 1 minus R. So minus -1/2, and when you minus a negative, it turns to positive. So 5 over 3/2. And of course, you can't keep that fraction within a fraction, so multiply, bring this up, multiply by the reciprocal, 2/3. Okay, so 5 times 2/3 is equal to 10/3. So the value that this will be approaching will be 10/3. Okay, 10/3 is the value that this approaches. Okay. Next we have number 73 from the book, where n equals 1, that's our lower limit, and our upper limit is infinity, because remember these are infinite series here. Our explicit formula is as follows. Notice Our R value is 7/3. So right away we can say this series diverges. Therefore, no sum exists. And the reason for that is the absolute value of 7/3 is greater than 1. Okay? That R value, the absolute value of R, is greater than 1. Therefore, this series must diverge. There is no sum. Okay, last example, 79. So we weren't given that sigma notation. We were given the sequence itself. So what we're going to have to do first is find out what R is. Okay, remember, you can take any two subsequent terms as long as it's given that this is geometric, right? If you're not given it's geometric, you better test all terms and make sure it works. But we were given it's geometric, so take any two subsequent terms and divide that second by the first, okay? So in this case, if I chose these two, I would take 4, so R equals 4 divided by 6. Okay, also I could have taken 9 and 6, I could have taken 4 and 8/3, so we'll test it. So 4 divided by 6 is going to simplify to 2/3. So R should be 2/3. Let's test these. Is 6 divided by 9 2/3? Definitely. If you took 8/3 divided by 4, it would also be 2/3. It should work for any set of subsequent terms. Divide that second by the first. So R equals 2/3. And then our A sub 1 is equal to 9. The first term is 9. So then, therefore, obviously, since R is 2/3, we know that this series converges, so we can go ahead and plug in. S equals 9, that first term, divided by 1 minus that ratio, 2/3. So then we would have 9 divided by 1/3. Of course, multiply by the reciprocal. So 9 times 3, which equals 27. So the value this series approaches, this geometric series approaches, is 27.